We have just witnessed the first launch of a completely new version of SpaceX's Starship. And with that launch, we also got a very clear glimpse into the future of human space exploration. But at the same time, this flight also reminded us that the road ahead is still very long. Starship's 12th test flight was spectacular and exciting, just like every previous flight, but it was far from perfect. At certain moments, things became quite messy. As usual with SpaceX, they did not get everything right on the first attempt. And because of that, this flight gives us a lot to analyze. This was the first Starship launch since October 2025. That means SpaceX had roughly 7 months of downtime between flights. But that period was not wasted waiting time. SpaceX used it to complete one of the biggest, boldest, and most revolutionary changes they have ever made to the entire Starship rocket program. This flight did not only feature a new Starship design, it also included a new super heavy booster equipped with new Raptor engines, along with a newly built and heavily upgraded launch pad. All of these elements were waiting for their first real-world test. Because this was a new system with so many changes, SpaceX had to cancel the first launch attempt. They went through the countdown and everything seemed to be approaching liftoff, but in the end they were forced to stop because one component was not working properly. Fortunately, the problem was not with the rocket itself. It was with one very specific part of the launch tower, the quick disconnect arm connected to the upper half of the rocket, the ship stage. That arm is responsible for delivering fuel into the ship's tanks. After fueling is complete, it is supposed to fold away from the rocket just before launch. But this time, that did not happen. A pin got stuck and prevented the arm from moving correctly. Because of that, the entire launch process had to be shut down. It was a disappointing issue, but it also gave us an early look at SpaceX's new fuel loading system on the upgraded launch pad. And that system is truly impressive. SpaceX can now fully fuel the largest and most powerful rocket ever built in only about half an hour. If you remember NASA's Artemis 2 launch earlier, that was also a very large rocket, but still smaller than Starship. Yet NASA took more than 3 hours to fully fuel it. That comparison shows just how important SpaceX's rapid fueling capability really is. When working with super-cold cryogenic propellants, time is critical. These cryogenic fuels are kept at extremely low temperatures, below -100 degrees Celsius. The rocket is not fully insulated, so the longer the fuel remains inside the tanks, the more it warms up, boils off, evaporates, and is lost. On top of that, SpaceX's long-term goal is to launch multiple Starships per day. If every fueling operation took several hours, that goal would be very difficult to achieve. So this new rapid fueling system is a crucial part of Starship's future operational strategy. By the second attempt on Friday, everything moved much faster. After the technical team worked through the night to fix the stuck pin on the quick disconnect arm, the entire system was reset. This time, the countdown proceeded smoothly all the way to zero. And finally, we got to see what this new version of Starship could actually do. The first thing that was easy to notice was that the launch pad looked completely different from before. In previous launches, Starship was basically sitting on a large metal ring with legs. Underneath it was a water spray system that looked like an upside-down shower head, spraying water upward while engine flames blasted in every direction. That was an interesting experiment, but it was not yet the complete solution. This new launch pad, however, is a much more serious system. Starship now sits on a strong structure made of reinforced concrete and steel. The water deluge system has been upgraded, spraying water directly into the base of the rocket. The enormous flame from the engines no longer spreads chaotically in all directions. Instead, it is diverted into 2 channels on the left and right sides. Those channels are also water-cooled. All of these upgrades are designed to make sure the terrifying power of the super heavy booster does not destroy the launch pad systems, something that happened quite often during previous tests. This directly connects to SpaceX's ultimate goal, launching many times per day without needing major repairs between flights. If every launch damages the pad, then Starship cannot become a rapidly reusable space transportation system. So the new launch pad is not just infrastructure. It is a key part of the entire Starship vision, providing all of that destructive power as a newly upgraded super heavy booster. From the outside, it may look fairly similar to earlier versions, but SpaceX has changed a lot at both the top and bottom of the booster. Let's start at the bottom, where the most violent action happens during launch. This booster is equipped with 33 brand new Raptor V3 engines. Every Starship flight to space before this used Raptor V2 engines. The earlier suborbital test flights used Raptor 1.0. When you place all three generations of Raptor engines side by side, you can clearly see the evolution. In theory, Raptor V3 should be more reliable, more powerful, and less likely to suffer unexpected explosions. But this flight was the moment when we would find out how that theory worked in practice. Raptor V3 is the version SpaceX hopes will become the near-final form of the Raptor engine for this phase of development. The most important improvement is not simply that it is slightly more powerful than V2. The real breakthrough is how much SpaceX has simplified the design. Many of the external pipes, wires, sensors, and components that existed before have either been removed or moved inside the engine itself. That is the big secret behind Raptor 3. Because of its cleaner and more compact design, the engine no longer needs to be surrounded by as much external shielding. That is why on the new booster, the engines appear almost completely exposed underneath. This allows Starship to save about 1 ton of mass per engine. And remember, the booster has 33 engines. If each engine saves roughly 1 ton, the total mass savings are significant. Those engines are also connected to a new fuel transfer tube. This tube runs straight down the center of the booster. The size of this fuel line alone is almost comparable to an entire Falcon 9 booster. It delivers a massive flow of methane directly into the engine bay. That is what allows the new booster to ignite all 33 Raptor engines at the same time. On previous flights, we usually saw the booster engines start up in groups. Power would build gradually section by section before the rocket could finally lift off. But this time was completely different. The new Starship seemed to leap off the launch pad in one powerful motion, then rapidly climb into the sky. After only about 30 seconds, the rocket had already reached a speed of more than 500 kilometers per hour and an altitude of nearly 2 kilometers. Compared with Flight 11, this new version appeared to be about 25% faster during liftoff. That allowed the rocket to climb through the lower atmosphere at record speed. And soon after, we reached one of the most exciting moments of any Starship flight: hot stage separation. This is another area where SpaceX made a major change to Super Heavy, especially at the top of the booster where it connects to the ship stage. Previously, there was a large adapter between the two stages called the hot stage ring. This ring allowed the ship to fire its engines while still attached to the booster. That way, the rocket never lost thrust on its way to space. But the old design had one downside. After stage separation, that hot stage ring had to be discarded into the ocean. That does not fit well with SpaceX's goal of maximum reusability. So on the new booster, the upper section has been redesigned to integrate the hot stage connection directly into the booster itself. You can see a rounded dome that forms the roof of the fuel tank. This is the area where exhaust from the ship's engines blasts directly during separation. SpaceX says the internal pressure of the fuel tank, combined with reinforced steel plates, should be enough to withstand the power of the 6 ship engines. Around that is a triangular tube structure that connects the booster to the ship, while also allowing exhaust gases to escape easily during the hot stage event. But this is where things started to go wrong. The 6 engines on the ship fired up and pushed the booster downward toward the left side of the frame. That was a little strange, because during Flight 11, SpaceX had said the most efficient method was for the booster to flip straight upward and backward. Before hot staging, the booster shuts down most of its engines so the less powerful ship can pull away. But immediately after the flip begins, the booster is supposed to relight all 33 Raptor engines to perform a boostback burn. This burn is extremely important because it slows the booster down dramatically and begins sending it back toward the launch area. And that is exactly when the booster suffered a serious failure. It tried to restart all of its engines, but many of them immediately flamed out. Just 1 second later, several more engines also shut down. In the end, only about 4 engines remained running in an attempt to perform the boostback burn. But even those remaining engines shut down earlier than expected. If you look closely as the booster falls out of frame, you can see what appears to be several things exploding in a very dramatic way. From that moment, we know the booster was traveling far too fast and had almost no way to slow itself down properly. So all we could do was watch the onboard camera as the booster spun and fell back toward Earth. The booster fell through the cloud layer. During that descent, it began heating up due to atmospheric re-entry. The shaking became more and more violent as air pressure increased. This should have been the moment when we got to see another super heavy upgrade, the new grid fins. Grid fins are the large lattice-like steering fins located near the top of the booster. They help control the booster's descent through the atmosphere. On previous Starship versions, the booster had 4 grid fins, but the new version has only 3. To compensate, each grid fin is about 50% larger and placed in a more strategic location to provide maximum control during descent. However, during this flight, we barely got to see that system perform its role. The only thing we saw was a burst of fire rising from the base of the booster, and then the camera feed disappeared. That is a strong indication that the booster may have exploded in midair. This has happened many times in Starship's testing history, so the signal is familiar. But it was not what people expected from this flight because the new booster was designed to correct those older problems. In theory, the new design should have helped SpaceX avoid repeating those issues. In practice, it seems they still need more time. Fortunately for SpaceX, they were not trying to catch this booster with the tower's chopstick arms during this flight. The original plan was only to test a water landing with the new booster before returning to the goal of bringing the booster back to the launch site. That means after this failure, SpaceX may need to repeat the water landing test on the next flight before returning to the goal of catching the rocket with the giant Mechazilla tower. After the booster ran into trouble, attention shifted back to space and the Starship upper stage. And here too, things did not go completely according to plan. The new Starship V3 looks almost identical to the previous V2 from the outside. At least, most of the external shape does not appear dramatically different. But there is one very important upgrade visible on the backside of the ship, near the payload door. There are 4 round ports sticking out. These are connection points for docking with another Starship and transferring fuel in orbit. This is one of the biggest challenges if Starship is to become a vehicle capable of traveling beyond Earth, to the Moon or Mars. Starship needs to be refueled before it can travel beyond low Earth orbit. We have known that for a long time, but until now we had never clearly seen physical hardware on Starship that would allow orbital refueling to actually happen. So seeing these connection ports is a very important sign. However, the biggest changes inside the new ship are not visible from the outside. Their purpose is to prevent mid-air disasters like the one seen with the V2 ship, when the vehicle exploded in space and then rained down over the Atlantic Ocean as a cloud of burning debris. SpaceX says upgrading to the Raptor 3 engine is a major part of improving reliability. That is why it was concerning when, only a few seconds after hot stage separation, one of Starship's 6 engines shut down. But this is where the good news truly began. If we remember earlier failures, they usually started with the ship losing one engine. Then that failure would spread like a domino effect. Other engines would begin failing, the entire rocket would start spinning out of control, and eventually the vehicle would be destroyed. That was the scenario many people may have expected when they saw one engine shut down this time. But that did not happen. The new upgrades appeared to isolate the failure to just one engine. The ship continued accelerating and reached its target velocity of around 27,000 kilometers per hour. After that, the 5 remaining engines shut down properly without any strange signs. This was a very significant success. It showed that even though there was still an engine issue, Starship now appears much better able to survive a single failure than before. A little later, there was another moment of concern when the ship began to rotate slightly. But it quickly became clear that this was not a sign of losing control. It was simply moving into a vertical orientation to prepare for the next major technology demonstration. The ship carried 20 Starlink satellite simulators. These were not real satellites, but metal masses designed to match the size and weight of future Starlink V3 satellites that Starship is expected to deploy in the future. These simulators were used to test the new payload deployment system. The mechanism works somewhat like a Pez candy dispenser, pushing the satellites out of the payload bay one by one. We had seen this system before on Starship Flight 11, but this time there was something new. After the 20 simulators were deployed, 2 additional special payloads were released. These were not just simple metal blocks. They carried sensors and, most importantly, cameras. Thanks to those cameras, for the first time, we were able to see the perspective of a satellite leaving Starship's payload bay. From that view, we could actually see Starship flying in space, and the image was extremely impressive. After completing the payload deployment test, the final major task was for Starship to attempt a successful descent. Just like previous flights, the ship was targeting a soft splashdown in the Indian Ocean, about 500 nautical miles off the northwest coast of Australia. Since the ship had lost one engine during ascent, and the booster had suffered a major engine restart failure, nobody was completely sure how the final result would turn out. Starship's atmospheric re-entry has become one of the most iconic visuals of the entire program. In the past, the space shuttle re-entered the atmosphere in a somewhat similar way, but at that time, it was almost impossible to capture live footage with the kind of quality we can see today. Now, thanks to Starlink, we can watch this process in real time, with video quality improving after every launch. The ship passed through the hottest part of re-entry and remained intact. After that, it began maneuvering through the atmosphere using its flaps. This is practice for the future, when the ship will not simply fall into the ocean, but will return to the launch site and align itself to be caught by the tower's chopstick arms, just like the booster. To do that, the ship must fly in a path somewhat shaped like a hook, then turn around in midair, relight its engines, flip upright, and descend in a near-hovering position. In this case, 2 of the 3 center Raptor engines successfully restarted. That was enough to bring the ship down to the water in one piece. After that, we saw the familiar scene. The ship tipped over and exploded after touching the water. This is something commonly seen in Starship's ocean splashdown tests. Before the entire ship was engulfed in flames, we got a brief look at the heat shield tiles. And this time, they looked very good. It may have been the cleanest condition we have ever seen after a Starship re-entry. Usually, these tiles come back burned, melted, full of holes, or with several sections missing. But on this flight, the V3 version appeared to survive re-entry very impressively. After all of that, the big question is, what happens next? The answer depends on the root cause behind the engine failures seen during this test flight. SpaceX is famous for being extremely ambitious. That is not a bad thing. In fact, that ambition is exactly what has allowed them to achieve many things that people once thought were impossible. But it also means there is always a lot of trial and error involved in turning complex systems into something stable and reliable. Usually, SpaceX can overcome major problems within the next 2 or 3 tests. So there is no reason to think they cannot do the same this time. However, this failure also means SpaceX cannot quickly move into more ambitious tests with the booster and ship. Goals such as catching the booster with the chopstick arms, reaching full orbit, deploying real satellites, or docking 2 starships together in orbit may take longer than expected. All of those next steps depend on one central requirement. SpaceX must master the Raptor engine. And to do that, they first need to understand exactly why the engines failed during this flight. In summary, Flight 12 was not a complete failure, but it was not a perfect victory either. It was an extremely important flight because it showed that many of Starship's new systems worked well. The new launch pad survived the rocket's power. Fueling happened quickly. All 33 booster engines started powerfully at liftoff. The ship continued flying even after losing one engine. The payload deployment system worked. Re-entry was very impressive. At the same time, the flight also exposed the biggest problem right now, engine reliability, especially the booster's ability to restart engines after stage separation. If SpaceX cannot solve this problem, it cannot move toward full reusability. The booster needs to restart precisely, slow down at the right moment, control its descent, and return safely. The ship also needs to keep proving that it can survive single failures without losing the entire vehicle. That is why Flight 12 is a very clear reminder of the true nature of the Starship program. Every flight is a massive lesson. There are moments of brilliant success, and there are failures burning in the sky, but all of them push SpaceX closer to the final goal: building a giant rocket system that can be rapidly reused, carry cargo, satellites, and eventually humans into orbit, to the moon, and even farther, to Mars.